Okay, page 433 to 436, Unit 5, L'Hopital's rule. You might be tempted to call it L'Hospital's rule, but it is not. There is no S between the O and the P. It is L'Hopital's rule. At the onset of our studies of derivatives, we use the limit to find a derivative. If you will remember, the definition of the derivative of a function f of x was given by the following limit. The limit as h approaches 0 of f of x plus h minus f of x all over h. In the same sense, L'Hopital's rule uses derivatives to find limits of certain functions, in particular limits that are of indeterminate form. In our studies of limits, we encountered limits of functions that were of this form. When direct substitution is applied to evaluate a limit, results of 0 over 0 or any combination of the infinities are referred to as indeterminate form. Let's take a look at an example of those formed earlier in the year and remember the methods we used to find the values of those limits. So, when we try to evaluate the limit below, we could use direct substitution. So the limit as x approaches 3 of 2x squared minus x minus 15 over x squared minus x minus 6. So we're going to directly substitute this. So the limit as x approaches 3, actually, don't need the limit notation anymore since we're just going to plug in 3. It's going to be equal to 18 minus 3 minus 15 over 9 minus 3 minus 6, which is 0 over 0, which is an indeterminate. So direct substitution gave us the indeterminate form 0 over 0. So we're going to refer to the beginning of the year when we algebraically factored and canceled and then found the limit. So when we factor out this function, get 2x plus 5 times x minus 3 over x plus 2 times x minus 3. So we could cancel out the x minus 3's. So we're just left with the limit as x approaches 3, 2x plus 5 over x plus 2. So now we can actually plug in and directly substitute. So we have 2 times 3 plus 5 plus 3 plus 2, which is 11 over 5. So now, today, we're going to learn a new way to find the limit of when we have indeterminate form, and that way is L'Hopital's rule. It makes finding a limit of this form easier by using derivatives. So L'Hopital's rule states that if the limit as x approaches a of f of x over g of x is equal to 0 over 0, or if the limit x approaches a of f of x over g of x is equal to some combination of the infinities, then we can find the limit as f approaches a of f of x over g of x by just finding the limit as x approaches a of f prime of x over g prime of x. So all we have to do is take the derivative of the numerator, the derivative of the denominator, and determine the limit from that. So we're going to use L'Hopital's rule on this very function, where f of x is my numerator and g of x is my denominator. So f prime of x is equal to 4x minus 1, and g prime of x is equal to 2x minus 1. So our new limit is the limit as x approaches 3 of 4x minus 1 over 2x minus 1. So when we directly substitute, we get 4 times 3 minus 1, and 2 times 3 minus 1, which gives us 11 over 5, which is the exact same answer that we got when we factored and canceled. So 2 other limits that we learned earlier this year were also in indeterminate form. Numerically, we investigated the limits below to find their values, our 2 trig limits. So in the boxes below, we're going to use L'Hopital's rule to validate the numerical derivation of the values of these limits. So earlier in the year, we found that the limit as x approaches 0 of sine x over x is equal to 1. So now we're going to validate that using L'Hopital's rule. So we know that f prime of x, which is my numerator, is going to be equal to cosine of x, and g prime of x is my denominator, it's just going to be equal to 1. So we'll have the limit as x approaches 0, cosine of x over 1, which is just cosine of 0, which is equal to 1. Similarly, for our other trig limit, we got that it equals 0. So looking at the numerator as f of x, our derivative of f of x is equal to sine x, and our derivative of the denominator is 1. So our limit as x approaches 0, sine x over 1 equal to sine 0, which was 0. So we want to use L'Hopital's rule to find the values of each of the following limits. I'm only going to find the values for 2 of these limits, and the other 2 you'll do on your own. So this middle limit, the limit as x approaches 0 of 7x minus sine x over x squared plus sine 3x, we're going to first start by directly substituting. What happens when I plug in 0 here? I should get the indeterminate 0 over 0. So that leads me to believe that if I find the derivative of my numerator, which will be 7 minus cosine x, and if I find the derivative of my denominator, which would be 2x plus 3 cosine 3x, thanks to chain rule, then I should be able to find the limit as x approaches 0. So limit as x approaches 0 of 7 minus cosine x over 2x plus 3 cosine 3x be equal to 7 minus cosine of 0 over 2 times 0 plus 3 cosine of 0, which is 6 over 3, which is 2. The other problem that I'm going to do is this problem down at the bottom, where we're going to need to use multiple applications of L'Hopital's rule. So you can apply L'Hopital's rule as many times as you'd like. You are not required to only apply it once. However, usually one time does the job. So for this problem, I want to first make sure that I do get an indeterminate when I directly substitute. So when I directly substitute 0, I get the indeterminate 0 over 0. So the derivative of the numerator is equal to negative 2 sine x plus 4 sine 2x, thanks to chain rule. And the derivative of my denominator is equal to sine x. So I'll have a limit as x approaches 0, negative 2 sine x plus 4 sine 2x over sine x, which when I directly substitute, I get negative 2 sine of 0 plus 4 sine of 0 over x. We all know sine of 0 is just 0. So we have 0 plus 0 over 0. So we still have the indeterminate 0 over 0. So when I run into that, I can just apply L'Hopital's rule once again to my limit. So now the derivative of this new limit is equal to negative 2 cosine x is 8 cosine 2x, thanks to chain rule, and the derivative of the denominator is equal to cosine x. So my new limit is limit as x approaches 0, negative 2 cosine x plus 8 cosine 2x over cosine. When I directly substitute, I get negative 2 cosine 0 plus 8 cosine 0 all over cosine 0. And cosine of 0 is 1. So we have negative 2 plus 8, which is equal to 6 over 1. So our limit is equal to 6. Okay. So now we need to remind ourselves how we evaluated limits at infinity. So we want to algebraically find the limit below as we did earlier in the course. So when we had limits at infinity, we looked for the highest degree in that rational function. In our case, the highest degree is x squared. So what we're going to do is we're going to divide every term in our function by x squared. So we have 4x squared over x squared minus 5x over x squared over 1 over x squared minus 3x squared over x squared. And when we simplify this, we get the limit as x approaches infinity of 4 minus 5 over x over 1 over x squared minus 3. So now, when we actually apply the limit to these terms, the limit of a fraction where the variable is in the denominator and there's no variable in the numerator is going to be 0. So we get 4 minus 0 over 0 minus 3, which is just negative 4 thirds. So now thinking back to precalculus, our knowledge of the existence of horizontal asymptotes, we want to validate this answer. So in precalculus, we learned that since the degree of the numerator and denominator are equal, the horizontal asymptote will equal their coefficients. So the degree of the numerator is x squared, and the degree of the denominator is x squared. So therefore, the horizontal asymptote is equal to the coefficients of the highest degree in the numerator. That coefficient is 4. The highest degree of the denominator, that coefficient is negative 3, which is equal to negative 4 thirds. So now we're going to use L'Hopital's rule to find this limit. So f prime of x is going to be equal to 8x minus 5. And g prime of x is going to be equal to negative 6x. So we'll have a limit as x approaches infinity of 8x minus 5 over negative 6x. Like I stated previously, you could apply L'Hopital's rule however many times you'd like. So if we apply it again, then f prime of x is equal to 8, and g prime of x is equal to negative 6. So we'll have the limit as x approaches infinity of 8 over negative 6, which is equal to 4 over negative 3 or negative 4. So now we're going to apply L'Hopital's rule to this limit, and then using our knowledge of horizontal asymptotes of rational functions from precalculus, explain why the result is what it is. So I'm just going to leave a little space for that explanation. All of our work is going to be on the left side. So our f prime of x is equal to 10x minus 1, and our g prime of x is equal to 9x squared minus 4x minus 3. So our new limit as x approaches infinity is 10x minus 1 over 9x squared minus 4x minus 3. So again, we're going to apply L'Hopital's rule. F prime of x is equal to 10, and g prime of x is equal to 18x minus 4. So our new limit as x approaches infinity is equal to, x approaches infinity of 10 over 18x minus 4. So we have a few options here. We can stop here and just apply what we know about what happens when the denominator is the only part of our fraction that has a variable. Or we could take L'Hopital's rule once again. Both options will lead us to the same destination. So if we take L'Hopital's rule once again, we get that the derivative of the numerator is 0, and the derivative of the denominator is 18. So the limit as x approaches infinity of 0 over 18 is equal to 0. So since the degree of the denominator is larger than the degree of the numerator, the horizontal asymptote will be equal to 0. Because the denominator will always get larger faster than the numerator. So on this last page, you have 4 problems where you're going to apply L'Hopital's rule to find the limit. I'm only going to work through the first 2 problems, and you're going to continue working through the last 2 problems. So first thing we want to do is identify what is the indeterminate if there is one. So if we're looking at the limit as x approaches infinity of ln 2x over 2 square root x, when we plug in infinity, the numerator will get really large. Also, the denominator will get really large. So both the numerator and the denominator will approach positive infinity. That is our indeterminate. So to use L'Hopital's rule, the derivative of the numerator will be 2 over 2x is equal to 1 over x. And the derivative of our denominator will be 2 over 2 root x, which is equal to 1 over root x. So our new limit as x approaches infinity is of 1 over x over 1 over root x. So using keep change flip, we actually have the limit as x approaches infinity of 1 over x times root x over 1, which is equal to the limit as x approaches infinity of square root of x over x, which we can actually rewrite as limit as x approaches infinity of 1 over root x. So using our rule, our denominator is the only section of our fraction that has a variable. So this limit will equal 0. Okay, so now moving forward, we want to find the limit as x approaches 1/2 of x cosine pi x over e to the x minus square root of e. When we directly substitute, we get the indeterminate 0 over 0. So f prime of x is equal to cosine pi x plus x times pi times negative sine pi x. And that's thanks to product rule, and chain rule. And g prime of x would be equal to just dx, since this is a constant, the derivative of a constant is 0. So our new limit is from x to 1/2 of cosine pi x minus pi x sine pi x all over e to the x, which is equal to cosine pi over 2 minus pi over 2 sine pi over 2 all over e to the 1/2, which is equal to 0 minus pi over 2 over e square root of e. So if I were to rewrite this as a mixed fraction, I get negative pi over 2 over root e over 1. I can rewrite as negative pi over 2 times 1 over root e. So my final answer is negative pi over 2 root. So I want you to work on these two limit problems on your own, and determine what those values must be after using L'Hopital's rule.